Hello everyone, welcome again to Modeling Methods in ME, and today we're going to be discussing for the first time the numerical approximation methods for first order initial value problems. So as we saw during last lecture, there's a number of analytical or exact techniques that would allow you to find the exact solution to an initial value problem. An initial value problem, remember, is just basically a differential equation, a first order ordinary differential equation in an initial condition. So we learned that if the equation is separable, then we can just simply integrate both sides. If the equation is not separable, then it's exact under certain conditions. Then we can find the solution. Then we found that there's ways, if the equation is not exact, to possibly make it exact through an integrating factor. And then we ended up stating that, well, if the equation happens to be linear, we will always be able to figure out that integrating factor and so that we can get an exact solution. Now it turns out that the great majority of first order initial value problems do not have an exact solution because none of these conditions apply, and therefore we need to figure out, or we need to set up a scheme by which we can somehow approximate the solution, and that's what we're going to try to go over today. So again, this is modeling methods in ME, and we are going to go over numerical approximation methods for first order initial value problem. And again, for these methods to work, the initial value problem, the differential equation, does not need to be linear. It just needs to be written in a generic form that for which we can implement these techniques. So let's look at what we can do. Again, the great majority of these initial value problems do not have an exact solution. We have a number of schemes or a number of methods that will help us find the exact solution for a narrow band of these types of problems. But in general, they do not apply. So if given this initial value problem, where we have a governing equation written in the form dy dt equals to some generic function of y and t, that determines what the differential equation looks like. Again, this generic function of y and t can be anything, so as to make this differential equation linear, nonlinear, homogeneous, non-homogeneous, constant coefficient, variable coefficient, so on and so forth. So this is the only requirements is the first order ODE. So it's an ordinary differential equation of the first order, so the highest derivative is 1. And an initial condition where y of 0 is some y hat not. So I'm given initial condition. All right. So the idea is the following. Now, in all these techniques that we learned last class, we were looking for the function, the solution, the exact solution, the closed form solution, analytical solution. This is the same name for the same thing. Remember that we started the class by stating that the solution to a differential equation is a function. So we're looking for that function. So now, instead of trying to find an algebraic expression for the solution y of t, which is ultimately the goal of solving this initial value problem, try a discrete distribution. That is, we're going to try to find yi at some values of ti such that I goes from 0 all the way to n final. All right? So basically, instead of finding an algebraic equation, a function, the function y of t, which is ultimately the solution of this problem, what we're going to say is that we don't need that. What we need is just a distribution of points. Y is a function of some discrete values of time. And I'm going to confine those values to a number nf plus 1. So there's nf plus 1 of these discrete values of time. In order to do that, I'm going to take and expand y of t in a Taylor series about time value Tn. All right, so if you remember Taylor series, and actually we've used this approach in this class before, what we attempt to do, what Taylor series basically does is takes any function, or it states that you can expand any functions as an infinite polynomial series. So basically any function, any continuous function that you have, you give it to me, whatever it looks like, whatever it is, sine, cosine, exponential, logarithmic, or whatever it is, I can take that function and express it in terms of a polynomial that has infinite number of terms. And that's an exact approximation if you include all infinite terms. Turns out that you can truncate it and make it an approximate function, a polynomial that approximately gets you to the original function. Now the problem here is that we don't have the function that we want to expand. We don't have y of t. That's what we're looking for. And even though that's the case, we're going to go on with these and say, well, all right, I don't have y of t, but I'm going to say y of t can be y at the expansion point Tn plus dy dt evaluated at point Tn times t minus Tn, that is the first order polynomial in the series, plus the second derivative of y with respect to t squared evaluated at Tn times t minus Tn squared divided by 2 factorial, plus the third derivative of y with respect to t cubed evaluated at Tn times t minus Tn to the power of 3 factorial, all the way to the kth derivative of y with respect to t to the k evaluated at the expansion point Tn, t minus Tn to the power of k divided by k factorial, all the way to k going to infinity. That's what Taylor says. So basically the series will emulate the function y of t as a polynomial with infinite terms, an infinite order polynomial, and then this is an exact representation of the function y of t, which again, by the way, we don't have. All right, and if we don't have y, we don't have dy dt, we don't have the second derivative, the third derivative, we cannot evaluate it anywhere. So what are we going to do with these? Now we're going to make an assumption here. First thing you can note about these Taylor series is that these denominators get really fast, really high, really fast. They're very large denominators because they have a factorial in it. So by the time you're in the fifth or sixth term of these series, that denominator will actually disintegrate its own term, make it almost negligible. So assuming that t minus Tn is small, that means that we are expanding in terms of a Taylor series, but we're only interested in evaluating this polynomial expression nearby the point of expansion, near Tn, right? So the difference between t, which is the generic value of time, and Tn, the point of expansion, is small. Then we can truncate the series after the second term because t minus Tn to the power of k is very small if k goes greater than 2. Right? So assuming that this difference is small, then the square of that difference is also small. It's actually smaller. And the cube of that difference is actually even smaller, and so on and so forth. Not only that, we're dividing by a factorial term, which makes that even smaller. So we're going to take a blunt approach here and say I am going to take the series right here and I'm going to truncate past this point. I'm going to say that y of t is approximately y now it's an approximation and not an equality anymore, y at Tn plus dy dt evaluated at Tn times t minus Tn to the power of 1, plus there's an error in this truncation of the order of magnitude of t minus Tn to the power of 2. The error in this truncation is proportional to this term right here. Whatever it is, whatever the difference is, it is proportional to that term square. Okay, and why not to the term cube or the term to the power of 4 and so on and so on? Because this one is significantly higher than this one, which is significantly higher than the next one, and so on and so forth. So the largest term in the truncation dominates. So the truncation order of this approximation is of the order of t minus Tn to the power of 2. This is called order 2 approximation. So order 2, the error of the truncation is of order 2 because it's squared. All right. Now, what I'm going to do is I'm going to solve for dy dt. So dy dt evaluated at Tn is then approximately y at t minus y at Tn divided by t minus Tn. And there's now an error of the order of magnitude of t minus Tn. It's no longer squared, now it's order t minus Tn because now it's divided by these. All right, so what am I saying here? Basically, this I'm kind of recasting the very definition of a derivative. A derivative is basically the limit when the denominator goes to 0 of y at t minus y at t 0 or Tn divided by t minus Tn. This is the very old definition of derivative. So technically, this is an approximation that will be more precise if I make this difference between Tn minus Tn small. Now, I am going to let t be Tn plus 1, or a time level right next to Tn, right after Tn. And then I'm going to make the difference Tn plus 1 minus Tn equals to something that we're going to call delta t. And this delta t is a time step. So basically, this leads us back to the following. So the derivative of y with respect to t evaluated at Tn is approximately y at Tn plus 1. So remember, we switched t with Tn plus 1 with a time level right after Tn minus y at Tn divided by the size of the time step between the two plus an error which is of the order of magnitude of delta t. And a shortcut for these is basically dy dt at n at time level n is approximately y at time level n plus 1 minus y at time level n divided by delta t plus an error of the order of magnitude of delta t. This right here is not the solution to the problem we're looking for. It's what's called the first order. And it's called first order because it's order delta t and not delta t squared, delta t cubed. It will be second order if this is order delta t squared and so on and so forth. Finite difference approximation of the first derivative. Okay, so this is an approximation to the first derivative of a function y of t at a point n, at a point in time n, or a time level n, which is the value of the function at the next time level minus the function at the current time level n, divided by the time step size in between, and the error in this approximation is of the order of delta t. That's what we call it first order, because it grows with the size of delta t. Basically, if you decrease delta t by half, you should expect half the error. If you increase delta t by a factor of 2, you should expect twice the error. It's linear. It's linear in approximation. All right. So now that we have this approximation of the first derivative, what we're going to do is go back to the ODE, the ordinary differential equation, which basically is given to us as dy dt at t is equal to some function of y and t, some known function of y and t. This is the differential equation that we're told to solve. Now we're going to take this and evaluate ODE at time equal tn, at time level n. So basically that is dy dt at tn is equal to f of yn comma tn. Nothing wrong with that. We're just taking the differential equation and evaluating it at a specific point in time. Okay. Now what we're going to do is use finite difference approximation of dy dt. So I'm going to take this finite difference approximation, I'm going to take this dy dt on the ODE, and I'm going to replace it with these. So basically this is y at n plus 1 minus y at n divided by delta t is now approximately equal to f of y at n comma tn. And furthermore, then I can solve for y of n plus 1 is now approximately yn plus delta t times the given function f evaluated at yn comma tn. And this is called the Euler's method for approximating the solution of an initial value problem. How are we going to do this? Well, this is a first order. Again, that means order delta t approximation method for first order ODEs. So it's a first order approximation method for first order ODEs, which means that it will give me an approximation to the solution in discrete form. Okay, that will be not exact, it will be approximate, because we use an approximation of the derivative, and that approximation of the derivative actually grows and decreases as delta t increases or decreases. So theoretically, if we make delta t infinitely small, this should be exact. But obviously, when we implement this on the computer, we cannot afford to make delta t infinitely small, because we cannot afford to do infinite number of calculations. So there's a trade-off there between the two. So the way this works is you start at t0 equals to 0, where y at t0 is equal to this given initial condition. And advance in time until a final time has been reached. You decide a priori how many time steps you're going to take, how much of the solution you want to know from the initial condition. You cannot know this forever. You cannot know this to time infinity, even though the solution theoretically exists all the way to time equal to infinity. You can only seek for the solution numerically all the way to a preset value of time, a maximum value of time. The solution, or the result, is a discrete collection of values yn at tn from n equals 0 all the way to nf. So it's very simple. The way it works is that you know what the solution is at time equals 0. So you start from n equals 0. This says that y1 is equal to y0, which you know, plus delta t, which is a preset value of the time step size that you pick, times the function, which is given as part of the differential equation, evaluated at y0, which you know, and t0, which is 0. And then you go from there. Then you increase n consecutively until you reach the final value time. So this approximation is order delta t accurate, which means that if delta t is halved, then the error bound is expected to be halved. Okay, that's what order delta t accurate means. That's what first order approximation means. It doesn't mean that you know the error, because if you know the error, then you technically know the exact solution. We don't know the exact solution, generally speaking, for this problem. But you know that, well, if you start this problem with some value of delta t and you get some result that is discrete, some collection of points in time, then if you decrease the value of delta t by a factor of 2, you should expect that the new collection of points that you got, more cluster collection of points that you got, is better by a factor of 2. That's what this means. All right. So let's proceed. Now, as you would expect, an ordered delta t approximation is not good enough. Okay, it's not good enough for several reasons, as we'll see when we try to implement these on the computer by programming this. It turns out that you would have to make delta t very, very small to get a good representation of the solution y of t, which means that you're going to have to perform these iterations many, many, many times until you get to a solution that is consistent, or a solution that is acceptable to you. So instead of actually using brute force and breaking that delta t smaller and smaller and smaller, we can come up with a higher order type of approximation, one where the representation of the derivative is not first order accurate, but maybe second order or third order accurate, so on and so forth. Again, using brute force is not a good option for many reasons. First of all, it will slow you down. And second of all, it might get to a point where you cannot physically, in the computer language speaking, reduce the size of delta t by more than what you already have, because you might actually be approaching machine precision. So because the computer has a limited amount of bits in which it can actually store information, and it has a limited amount of memory for doing so, and the representation of real numbers in the computer is accomplished by this floating point scheme, for which you use a finite amount of bits. If it's single precision numbers, you use 32 bits, and if it's double precision numbers, you use 64 bits or 8 bytes, because you have this limited amount of storage information or storage space, and you have this limited amount of or limited amount of number of bits to describe a single number. Then the machine has an inherent precision. It basically means that there's a number somewhere in the computer to which that you add to another number, and actually it makes no difference, because you've actually approached machine precision. In the case of single precision, you're talking about 10 to the minus 11. In the case of double precision, the limit of singularity, or the machine precision, is closer to 10 to the minus 18. That's not the smallest number that you can represent in single or double precision. That is the actual machine precision. It's a number to which you add to another number, and actually it's not recognized. So we need to derive, because of these and other reasons, a higher order method. And for these, we need to go back to the Taylor series and truncate after the third term. instead of truncating after the second term, let's see what happens if we truncate the Taylor series after the third term. So that is yn plus 1 is now approximately y of n plus dy dt at n times delta t plus the second y and dt square times delta t square over 2 plus an error in the order of magnitude of delta t to the power of 3. Okay. Now, in order for these to be implementable anywhere in the solution of these given initial value problem, we need to somehow look at the second derivative, which we don't have in the ODE. However, if you go back to the ODE, we have dy dt is equal to f of y and t. We can differentiate the ODE, and then this will be the second derivative of y with respect to t squared is equal to the derivative of these with respect to time. But because this is a function of time and a function of y, then we need to do partial derivatives here. We actually need to do a chain rule. So the second derivative of y with respect to t is the derivative of f with respect to t, which happens to be the f dt times, I'm going to add the y and t here, dt dt plus the f dy of y and t times dy dt. So see what we're doing? We're basically using chain rule to approximate the differential of f as df dt times dt, partial of f dy times dy. And when we divide by dt, this is what we get. Obviously, these goes to 1. And obviously, this one right here is f of y and t per the original equation. So, therefore, the second derivative of y with respect to t squared is equal to the f dt as a function of y and t plus df dy as a function of y and t times f as a function of y and t. All right. So what we're going to do is plug these back into the expansion. So plug these into the truncated Taylor series. And what we'll have is y at n plus 1 is approximately y at n plus delta t times dy dt, and dy dt being f, so this will be delta t times f of yn tn plus delta t squared over 2 times this whole thing, df dt yn and tn plus df dy at yn and tn times f at yn and tn. This, as you can see, is another so-called explicit method by which you can get discrete values of the solutions at future times. You start at time equals 0. y0, you know, that's the initial condition. You can evaluate f at the initial condition and time equals 0. You can find the f dt because f is given, so you can calculate the partial derivative of f with respect to t and the partial derivative of f with respect to y. Evaluate those at the initial condition and at initial time, which is 0, or you can start from any initial time you want. Evaluate the f dy, evaluate f, and then this right-hand side is entirely known, and that will give you the solution at time step 1, at time level 1. Then you can advance the value of n to n equal 1, so that you can find y at n equal, you can find y of 2, and so on and so forth. This is called the Euler's second order. That means order delta t squared approximation method for first order ODEs. the process is identical. So start at t0 equals 0, where y of t0 is equal to the given y0. That's n equals 0. And advance in time n equals 0 all the way to some final value time. So you're going to perform nf time steps, so you can find nf plus 1 values of the solution y at nf discrete values of time by implementing this explicitly. So this is an algorithm that would take probably 3 lines to code. The first one will take 3 lines, this one will take maybe 4 lines because you have to evaluate these 2 things. But they're extremely simple. And the advantage is that this is order delta t squared, meaning that if you reduce the size of delta t by 2, your expected error should be actually smaller by a factor of 4. If you reduce the size of delta t by a factor of 10, you should expect your error to be 100 times better, 100 times smaller. So this is much better in terms of approximating than the original Euler's method. The problem with this method is that in order for you to be able to implement it, first of all, you need to calculate this partial derivatives of the function f, which is given in the differential equation. That should not be a big deal because this is normally well defined. But sometimes the differential equations are not explicitly given in terms of algebraic functions. Sometimes these differential equations are actually given in terms of also discrete representations. They're given in terms of data tables, or sometimes of databases. So you can actually query the function f at values of y and t. So when that's the case, then it becomes a little bit more complicated to calculate partial derivatives of that with respect to time and partial derivatives of that with respect to y, to the solution. So this is more of a method that can prove the concept of having a modified Euler's that has a higher order approximation, that you don't have to actually reduce the signs, you don't have to granulate time so thin, or so small, and you get an approximation that is actually quite good. Now, instead, what we're going to do is we're going to pack, as you can imagine, we don't need to stop here. We can take this Taylor series and keep adding terms, so basically truncating the Taylor series at a later and later term. And if you keep doing that and coming up with these approximations, you can find higher and higher order methods. And these methods will basically be solving or approximating the solution to the same problem. Okay, this method and this method, the original Euler, they actually are attempting to approximate the solution of the same problem. One uses a simple equation, the other uses a slightly more complicated equation. This one will give you a solution that is order delta t accurate, and this one will give you a solution that is order delta t squared accurate. So it's 1 order of magnitude more accurate. So you can imagine that an equation like this might exist for an order delta t cubed method or an order delta t to the 4th, and so on and so forth. So when do we stop? Well, turns out that there's a trade-off, as you can see, of the technique or the scheme being 1, efficient, 2nd, accurate, 3rd, stable, and also being computationally compatible, something that you can actually efficiently program. It turns out that that would happen at around order of magnitude number 4. So when the method gets to be order delta t to the power 4 is when we have found that actual sweet spot between this trade-off of computational efficiency and stability and accuracy and so on and so forth. Now, locally, all of these has already been derived for us. So we can pack different order methods into the so-called predictor corrector schemes. So what this is, it goes as follows. So again, given the IVP, so we are given an initial value problem that consists of a governing equation, dy dt is equal to f of y and t, where that function f is given. We know what the equation looks like. And an initial condition that says that y of 0 is equal to y naught hat. It's known. So technically we should put a hat on top of f because we know what f is. But that will confuse it with something else. So let's just leave it as f. So the discrete or the discretized solution yn at Tn such that n goes from 0 to some value nf may be approximated as, well, the first method that we learned is called the Euler's method. So we already know what this looks like. We know that this is order delta t. And this one goes like this. K1 is equal to delta t times f of yn comma tn. And yn plus 1 is equal to yn plus k1. Oops, this is 1, k1. All right, so this is the order delta t method. That's the same as the Euler's method. If you compare that a couple pages ago with the Euler's method, that looks identical. It's just broken up into this step that's called the predictor corrector step. You'll see what that means a little bit more clearly when we write the modified Euler's method. Which is order delta t squared. This method, calculate k1, which is delta t times f evaluated at yn comma tn. Then k2, which is delta t times f evaluated at yn plus k1, comma tn plus delta t. And then y at n plus 1 is y at n plus 1/2 of k1 plus k2. This is not the same as the second order Euler's method that we just derived, but it's very, very similar. And basically, it's order delta t to the 2. It's order delta t squared. So essentially the error decreases quadratically with a decreased value of delta t. This is called a predictor corrector scheme because K1 is essentially a predictor. K1 is equivalent to calculating the Euler's prediction, the first order prediction. Then you use that information, put it back into the equation to correct it, and that K2 is a corrector. And then you take an average between K1 and K2, and that's how you predict your next value of y. And then you advance in time. You make n equal n plus 1. Okay, so you start with n equals 0, for which you know the initial condition and you know Tn. Tn is equal to 0, obviously, at time equals 0. You predict the value of the solution K1, then you use that prediction here to correct the solution at K2, and then you take an average of the two, and that's the solution at the next value of time. Y1 is equal to Y0 plus 1/2 of K1, K2. Again, this is equivalent. It's not the same. It's not exactly the same as the second order Euler's method that we just derived, but it will produce an equivalent solution. More importantly, order delta t square accurate. Again, this doesn't stop here. We can keep going. There's an actual method that's called Hoynes that happens to be order delta t square also. It's not order delta t cube. It's not third order accurate. In this method, you calculate K1, the predictor, exactly the same way. Then you calculate the corrector, but instead of correcting at all the way through K1, you say this is delta t times f yn plus 2/3 of K1, comma Tn plus 2/3 of delta t, and the solution at the next time value is equal to the solution at the current time level plus 1/4 of k1 plus 3k2. So 25% of the predictor, 75% of the corrector. And again, this is not arbitrary. These particular parameters here and the solution schemes are not arbitrary. These are found by implementing, again, a finite differencing approximation of the first derivative, the second derivative, even the third derivative or the fourth derivative, depending on the order of the method. And you get to this point where encapsulated in this types of schemes are called predictor-corrector. This looks like this. Now, the most widely used one is called the Runge-Kutta Method, due to Runge and Kutta. These are actual, Kutta was an aerodynamicist, a physicist, engineer, aerospace engineer. Aerospace engineering didn't exist back then, but it was a mathematical physicist and engineer that was looking at aerodynamic profiles, and Runge was a mathematician. And they came up with a scheme to solve these boundary layer equations that rely on a fourth order approximation of the derivative. And they found it to be very robust, very stable, very efficient, and actually hits that sweet spot that we're talking about between efficiency, stability, accuracy, and computational viability. So this one has a predictor, and it has 3 correctors. The first corrector uses this k1 at 1/2 of its value and 1/2 of the time step. The second corrector, k3, utilizes the second corrector, or the first corrector, I'm sorry, halfway through k2 and tn plus 1/2 of delta t. Then the third corrector, so 1 predictor and 3 correctors, the third corrector, k4, is delta t times f yn plus k3, comma tn plus delta t. And finally, the solution, yn plus 1, is yn plus 1/6 of k1 plus 2k2 plus 2k3 plus k4. Again, it doesn't end here. You can come up with your own scheme. Again, those parameters are not arbitrary. They need to be compatible with the Taylor series approximations of several order derivatives. But you can come up with your own scheme. It just turns out that this one actually hits the sweet spot. It's the most widely used one. It's order delta t to the 4th accurate, essentially meaning that if you reduce the size of the time step by a factor of 2, you should expect an error that is 16 times smaller. Okay, that's an error bound. Again, you don't know the error, because if you knew the error, there's no need for looking for an approximate solution, because if you knew the error, that means that you know the exact solution. You don't know the exact solution. So, but it gives you the error bound, the area from within, or the range in which the solution actually satisfied, and the solution is within the exact solution, and that actually decreases by in the order of delta t to the 4th. Also, that means that if you change your delta t, if you shrink your delta t by a factor of 10, if you make delta t 10 times smaller, you should expect an error that is 10,000 times smaller than the one you got on the previous approximation. All right, so let's implement this. Let's look at these. And to implement these, what we're going to do is look at a differential equation of which we know the exact solution. Now, if we know the exact solution, it makes no sense, no point on looking for an approximate solution. Why we're going to look for 2 solutions? We already know the exact one. Well, the point that we're trying to make with these illustrations, this example, is for the purpose, again, of illustrating the technique, is let's find a problem of which we know the exact solution, then find the numerical solutions, and then compare them one by one to these exact solutions to see which one's better. Well, obviously, we should expect the Runge-Kutta to be the best one, but who knows? Let's find out. So, example. Given the IVP that is defined by the governing equation dy dt as a function of t is the sine of 2t minus y times the tangent of t, with the initial condition that y is 0 is equal to 1. So we have these equations. So this is f of y and t. So f of y and t is this whole thing. Notice that this is a linear equation. It's a first order equation, obviously. It's linear because y does not show up as in different powers or multiplying derivatives or in the argument of a transcendental function or anything. It multiplies a variable coefficient, the tangent of t, and it's non-homogeneous because the right-hand side term, the independent term, sine of 2t, is non-zero. That's what makes it non-homogeneous. Initial condition is also non-homogeneous. It's different than 0. So at time equals 0, the solution is equal to 1. Now we can find, I should say easily, but yes, we can find an exact solution to these linear initial value problem using integrating factors. And that solution is y of t is equal to 3 cosines of t minus 2 cosine square of t. That is the solution to this problem. Again, this is an illustration example. If we know the exact solution, why are we looking for an approximate one? This one's better already. This is, again, to illustrate the power and the precision of these numerical techniques. Now, if you want to go home and after these lectures over and corroborate that this is indeed the exact solution of these, all you need to do is differentiate it and then compare left and right, and you'll see that it matches. You'll get an identity. So we're going to approximate the solution numerically using the 4 predictor corrector schemes. Okay, there's not 4 predictor corrector schemes. There's many more than 4, but I just show you 4, so we're going to use this 4. So that f of y and t, so the differential equation is equal to f is equal to the sine of 2t minus y times the tangent of t. Okay, this is what defines the differential equation. Okay, we're going to assume that we don't know the exact solution. We're going to just depart from the differential equation, and we're going to let the final time of evaluation be 1, whatever that is, seconds, years, days, whatever that unit of time we're working on. I don't know what this function represents. If it's the vibration of a string or the growth of some factor or the transmission of some disease is governed by this equation. Who knows? So TF is equal to 1. We're going to leave everything non-dimensional. And we're going to select n so that delta t is equal to TF divided by n. So we're going to select the number of time steps, nf, or just n simply, and make the size of the time step equals to this final time divided by the number of steps, obviously. So note that I am leaving it at TF equal 1 because note that f of y and t is singular at t equals pi halves, 3 pi halves, etc. So at 90 degrees, 270, and all pi halves multiple of that, this is singular because the tangent of 90 degrees is infinity, and the tangent of 270 degrees is minus infinity, and the tangent of 540, and so on and so forth, is singular. Therefore, numerical schemes will break down at these values. we'll address that later, but when it comes to singularities, numerical schemes have to be very specifically treated. You cannot just tell the computer, evaluate this at pi over 2 or a time that is very close to pi over 2, because then the computer will blow up. It will actually not blow up, but give you an error that is not a number, and it cannot continue. Even though the solution, obviously the exact solution is perfectly well behaved. The exact solution is only in terms of cosines, even though the differential equation has some singularities in it, by evaluating time at certain locations, the exact solution is perfectly well behaved. Okay, so we're going to implement these in Mathcad. For the first time in this class, we're going to go to Mathcad and try to implement something. And again, I've already posted some sessions of me explaining how to use Mathcad and introducing the package and what it does and what it cannot do and so on and so forth. And what we're going to do today is just implement these particular problem in Mathcad. All right. So let's go. I've already opened the Mathcad file, and I'm going to share this with you. So this is numerical approximation methods for first order initial value problems. Again, the ordinary differential equation is defined by this function of y on t. This is technically what we know. Sine of 2t minus y tangent of t, and the initial condition is equal to 1. So let me start from 0 in case you haven't watched my videos. So Mathcad is, again, what you see is what you get mathematical interpreter, mathematical spreadsheet interpreter, which means that everything you write will be interpreted from top to bottom, from left to right. So I'm going to write the function of y and t function. Something is preventing me from writing f. Just going to write it here, f of y and t. And then to define something, if I say equal, it doesn't know what it is because it's just trying to evaluate what f of y and t is. So it's giving me an error, just saying f and red. I don't know what that is. I have to press column. So it introduces column equal. This is a definition equal. And this function is the sine of 2 times t. It is very important that you write the times, t, 2 times t. So don't say 2t because it would not know what it is. It would assume that 2t is another variable. Minus y times the tangent of t. Okay, that is the function that defines the differential equation. Now this down here is the exact solution. And now the exact solution is given by this function that we can do this by hand and determine what the exact solution is, that we are only going to use this for the purpose of comparing these approximation solutions. The initial condition, y, I don't know what this is not letting me write, so y, and I'm going to introduce these subscript. The subscript 0, or y naught, is equal to 1. Okay, so I'm going to move this here. Again, remember, Mathcad knows how to interpret things from top to bottom and from left to right, so it's very important that you line things up. And I'm going to define the final value of time for evaluation. Again, TF T dot F is equal to 1. Now T dot F just basically means, I'm going to move this whole thing one indent a little bit to the right because it's having some problem. Okay. All right, so I'm going to say then that the number of time steps that I'm going to use, I'm going to start with a very coarse time step distribution from time equals 0 to time equal 1. Remember, 0 is at the initial condition. 1 is the final time step where you're interested in knowing the solution, the final time value in which you're interested in knowing the solution. I'm going to say there's only 10 steps in between. Okay, that's very coarse distribution. That means that delta t, the size of the time step, is equal to tf over n. I'm going to redefine that again, so you see how it goes. So delta t, and by the way, to introduce the sign delta, delta is capital D in Greek. So I say D, Control G, and it turns it into Greek. Delta t, by the way, you don't need to call it delta t. You can call it whatever you want. You can call it h, which is in the literature is an expression that is commonly used, is equal to tf divided by n. Okay. Then I'm going to declare a variable n. I don't know what's happening here. Maybe it's the Zoom that I'm using. Let me see. I guess so. So I'm going to say n is equal to a range variable. I'm going to define n as a range variable that goes from 0, 1, all the way to n. And by the way, to introduce a sequence, I don't say period, period, I say semicolon. So this basically introduces or creates a range variable n that goes from 0, that has whose second element is 1, and the last element is n. I could have actually omitted the second element because by default Mathcad assumes that the second element is separated by the first element by an integer value 1. And it would have been exactly the same. So I could say 0, 1 all the way to n, or just 0 to n. So if I query the value of n, all I get is this collection, a range of numbers from 0 to 10. Okay, this is called a range variable. So now n doesn't have a single value, it has a range of values. It's not a vector, it's a range variable. I am going to define t as a vector, however, and yen as a vector. And the way this works is as follows. So I'm going to say t, I guess it doesn't want to write t either, t so t, and left square bracket, now it opens up a subindex, not a subscript. A subscript is just for illustration, just to write tf a little bit nicer, where f is just a subscript of t. If I want to write a subindex, then tn is equal to n times delta t. And what that does, if I query, escape, interrupt this calculation. If I query what t is, I'll do it here on the right hand side. T is a vector that is indexed by n from 0 to 10, that has values 0, 0.1, 0.2, which is the separation is essentially the value of the time step. By the way, after I define something, I can just query its value, say equal, and it'll tell me what the value is. All right, then I'm gonna create another vector of values, ye, y dot e, so just to denote that this is the exact solution, left bracket n, so indexed by the same subindex n, is equal to the exact solution y evaluated at each of the values of tn. So if I query what y is, ye is equal to, and I'm going to move it here to the right hand side. So ye is also a vector or an array. It doesn't want to show right there. That is indexed by 11 values from 0 to 10. That has values 1, 1.005. That is technically the exact solution evaluated at these 11 values. Okay, starting with 1, which is the initial condition. Obviously, this exact solution not only has to satisfy the governing equation, but it also has to satisfy the initial condition. All right. Let me save this. So I want to plot the solutions, and then to plot the solution is very simple. In Mathcad, you don't have to invoke a new window or anything like that. You just say insert, you say graph, and I want an XY plot. And for some reason, it doesn't want to display again. So there it is. So this is a plot. And on the x-axis, I'm going to type t sub n. And on the x-axis, on the y-axis, I'm going to type ye sub n. And then I can do all kinds of things to these plot. Like, for example, the way I had displayed it, I can put grid lines on the x-axis. I can put grid lines on the y-axis. I can change the scheme. I can change the number of grid points and the solution. I can change the colors of the traces. I can double click on the trace itself and change the color of the trace or the weight of the lines or the type of line, or just use symbols and so on and so forth. So you can play with these. And again, that's all in my videos of explaining how to use Mathcad. All right, so the Euler's method, I'm going to try to do it right next to this one here, so that to make sure that I can type somehow Mathcad when maybe it's conflicting with the recording studio. So the Euler solution, again, y dot Euler, which is just simply a subindex, is defined as, and I'm going to use the programming tab. You can change, you can add tabs or close or hide tabs. And the programming tab is the one that is going to allow you to do this iteration process right here. So I'm going to add a line. I'm going to say the 0th value of y is, so y left bracket 0 is the given value of the initial condition, which is y dot o, which we define up here to be 1. And now we're going to add a line, and in this line we're going to loop using the for function. Don't type for, you have to use the function from the programming tab. And within the range going from 0 all the way to n minus 1. And add a line. Calculate the predictor. K1 is equal to delta t times the function f evaluated at y left bracket n comma t left bracket n close parenthesis. That's the predictor. And then the solution. Remember, the first order Euler's method only has a predictor. It doesn't have a corrector. Y at n plus 1 is equal to y at n plus k1. And internally I can use whatever variable I want. I can use y, I can use x, I can use z, whatever I want, but I have to return that value. And when I return that value, which is essentially an array of values, I return it, and it now becomes y.Euler. That's it. I've programmed the first order Euler's method here. And if I query y.Euler, what I will get is 11 values starting at the initial condition, that's index with 0 all the way to index with 10, index at 10, the initial condition, and then the approximations given by these scheme all the way to the 10th time step. Then I'm going to plot these. And again, I don't know why it's not plotting. Let me bring this one into here. Okay. I guess it's all right. So after I create the new array y Euler, I can actually plot it in the same plot here. I can create a plot and add elements to the x-axis and to the y-axis, as long as I separate them by commas. And I already played here with the traces, so that the first line is just a solid red line indicating the exact solution, while the second is not a line, it's just a collection of symbols, and I'm using diamonds, blue diamonds for that, to indicate that this is a numerical approximation, and to also indicate that the numerical approximation is not a continuous smooth distribution or an algebraic function. It's just a collection of discrete values, 11 values in this case, from 0 to 1. So these are the discrete values, and as you can see, they tend to approximate the solution, but not very well. They're approximated, it's initially undershooting the solution, and then when it gets to a point where the solution actually, where the solution starts to decrease, it tends to overshoot the solution. Now, to quantify, this is a visualization of the solution, which provides you a qualitative representation of the quality of the solution, of the preciseness of the solution. To be able to really quantify how accurate the solution is, we can calculate a residual. And a residual is nothing but the standard deviation between the two solutions, basically the sum of the squares divided by the number of points, the sum of the square of the differences between the exact and the approximate solution divided by the number of points, square root, so that's standard deviation. And what I'm doing is I am normalizing that standard deviation with the maximum value and the minimum value of the exact solution, so that I get a number that is non-dimensional. So I'm taking the standard deviation of the difference between the two solutions, dividing it by the solution itself, the maximum and minimum value, the span of the solution, and then I am calculating a percentage. And to calculate a percentage, if I remove the percentage from these, all I get is a number like this, 0.115. This is a normalized value of the standard deviation, right? Non-dimensional value of the standard deviation. If I put a percentage here, it will tell me these solutions are actually the residual between, or the error, it's also called the L2 norm error between the two solutions, is 11.491%. I can increase the resolution of these, I can increase the number of digits, I can just double click on this, and I can say add decimal places if I want to, or use scientific notation, or whatever I want. There's a lot of things that I can do in here to visualize this a little bit differently. Now the rest of the schemes are programmed quite similarly. The next scheme is going to have a predictor and a corrector. This is the modified Euler, which I call mod Euler. Again, it's going to produce an array with 11 values, nothing different than the regular Euler. So y mod Euler is equal to 11 values from 0 to 10. But notice that those 11 values are actually much more accurate with respect to the exact solution. So the second order scheme is already much more accurate, and it produces a residual that is 1.915. It's almost 10 times better than the residual produced by the Euler's method. The Hoynes method, which is also order delta t square accurate, second order accurate, has a predictor and a corrector, and it produces also what's at least qualitatively looking like a very good solution. If I quantify the error using this residual, I notice that the error is actually smaller than the modified Euler. Now, the Hoynes is not necessarily more accurate than the modified Euler. They're both delta t square accurate. It's just that the Hoynes will work better for certain classes of problem than the modified Euler will. And ultimately, I can use the Runge-Kutta for, which actually calculates a predictor and 3 correctors at every time step, at every step of this loop. And then it actually uses that to calculate, to approximate the solution at the next time level, yn plus 1, returning, if I say what is y rk4, it's just 11 values in this case, because I've already preset the number of time steps from time equals 0 to time equal 1 to 10. I can actually modify the number of time steps, as we'll see in a minute. And this produces an error that is 1.963 times 10 to the minus 3%. So the error is actually 1.9 times 10 to the minus 5. It's a very tiny error between the exact and this numerical solution by just implementing 3 additional correcting lines in the scheme to yield an order delta t to the 4th error. Now, what I wanted to convey here is that the error is not necessarily the exact error between the numerical solution and the exact solution. Because if you know the exact error is just basically the difference between the two. But if we knew the difference between the numerical approximation and the exact solution, that means that we know the exact solution. In this particular problem, we happen to know the exact solution because this problem is for illustration purposes. But if I would only were to give you the differential equation and the initial condition, all you have the hope to find finding is the numerical approximation. And these is going to give you a bound on the error. This order delta t or order delta t squared is just basically how much the error increases or decreases depending on how you change the delta t. All right. So if I go back here and say I now want to make this 100, I want to use 100 values of time between 0 and 1 seconds, or 0 and 1 year, whatever that 1 means. That means the time step size is 0.01. It's 1/100th of a second, or 1/100th of a day, or 1/100th of a year. The solution looks exactly the same. The exact solution hasn't changed. What will change is the approximate solution. Look, even the Euler solution is very good. At least qualitatively, it looks very similar to the exact solution. And if we want to find a quantitative expression for the solution, we look at the residual, which was originally 11.491% when we use only 10 time steps, and I can actually update this value using F9. It's now 0.995. So we went from 11 to 1 order of magnitude. We changed the value of the time step, we'll change the size of the time step by a factor of 10. The error decreased by a factor of 10. Not exactly, because remember these are error bounds, but the order of magnitude is now better, a factor of 10. It went from 11 to 1. Same thing, the modified Euler's method, before, when we only had 10 time steps, it was 1.9%. If I update this value using F9, now it's 0.016%. Again, 10 times better. I'm sorry, 100 times better. We change the value of delta t by 10. We expect the error to be 100 times better, 10 squared. So before it was about 1.9, now it's 0.016. So it's 2 orders of magnitude better. Same thing for the Hoynes method. Before it was 0.4%, now we expect this error to be 100 times better, so 0.004%. So I'm going to update this. So it's 0.003. So we are within that order of magnitude bound. And in the Runge-Kutta, if we decrease the size of delta t by a factor of 10, now we expect the error to decrease by a factor of 10,000 by 4 orders of magnitude. So if I update this, I should find something in the order of 10 to the minus 7. So if I update this, there it is, 1.5 times 10 to the minus 7. So this is what I wanted to show you today. This is a basic illustration of how to program and implement these numerical approximation schemes for the solution of first order initial value problems. And again, we packed them all into these so-called predictor corrector schemes, starting with first order methods like the Euler's method, second order like modified Euler and Hoynes, and fourth order like Runge-Kutta. And as you can see, the higher the order, the better. Okay. Again, we can keep going up in order of approximation, but again, you'll find some errors that we'll start introducing, not truncation errors, but we'll start introducing other types of error that would affect the accuracy and the stability of the final solution. So thank you for your attention, and I'll see you next class.